Let's begin with the today's session. So, can we start with today's session? Okay. So, welcome everyone to the NPTEL course on Introduction to Polymer Physics. The course is instructed by Professor Amit Kumar, Department of Chemical Engineering, IIT Guwahati, and I am the teaching assistant of this course. My name is Shikha Sharma. I am a research scholar in the Department of Chemical Engineering, IIT Guwahati. So we have till now covered, we have gone through 6 weeks already. Now today it is a live interaction session for week 7, which is on the topic viscoelasticity and rubber elasticity. So I hope you have gone through 3 lecture videos on this topic already. So in the last class uh, we have covered the amorphous polymer phase. In that we have covered the glass transition temperature and how are the different factors which are affecting glass transition temperature. And then we discussed about the differences between the crystalline polymer phase and the amorphous polymer phase. We also discussed about the free volume concept. We discussed about the thermodynamics of glass transition in an amorphous polymer phase. And in the crystalline polymer phase, we understood that how the crystallization happens through the help of the nucleation and the growth, and how the spherulites will form, and what is its role in the structure of the crystalline polymer. And then we discussed about how to calculate degree of crystallinity and by various different equipments. And then we discussed about the kinetics of the crystallization using the Avrami equation. And then we discussed about the it's sorry, the spelling is mistake here. It's Avrami. So it will be this, yeah. So after that we discussed about the melting and melting temperature. And then we discussed about the mechanical properties of the polymers like the stress strain curve, and the area it defines the toughness and the different in the different materials like elastomers and others, how the mechanical properties will be there in the polymers and the elastomers. And then we discussed about the elastic deformation of polymers. So all these topics we have already covered in our previous lecture slide, which is of week 6. Now, in the week 7, which is today's interaction session, we will be trying to cover the topics like viscoelasticity and the mechanical models like Maxwell and Kelvin-Voigt models. And then we will going to understand how the rheology in a polymer acts like basically polymer rheology is related to the non-Newtonian behavior. It does not show the Newtonian behavior, whereas it shows non-Newtonian behavior. So we will discuss the non-Newtonian behavior and rheology of the polymers, and then we will trying to cover the rubber elasticity, and in that we will try to understand uh, some of the numerical problems also. So uh, uh, all these 3 topics we will be trying to cover, and we will try to uh, solve some of the concepts and uh, discuss some of the concepts and solve some of the practicing problems. And then uh, we will understand the like in the questions also, there are some questions also, and in from that questions we will try to understand how to solve that, and and also we will understand the concept through those numerical problems. And if you have any doubt in the previous lecture slides or in the today's lecture slide, please feel free to ask, because I think your exams are near. So please, if you have doubts, please ask, and we can just take those questions and solve. Okay, so let's begin with the first problem of today interaction classes. So first question is, if a constant stress is applied and the strain is monitored with time for a viscoelastic material, which of the following is true? A. Strain will develop instantaneously and remain constant thereafter. B. Strain will always increase linearly as long as the stress is applied. C. Strain will increase as long as the stress is applied, but rate of strain will change with the time. And D is, if the stress is removed, the strain will instantaneously become zero. So this problem is basically related to how a viscoelastic material, our polymer is basically, it is a viscoelastic material. It is neither completely elastic nor completely viscous material, right? So it is a viscoelastic material. So in this question it is being asked that if a constant stress is applied and then we need to monitor the strain with the time, so how it behaves. We have these four options. Anyone please would like to answer? This is a very basic question. D, C. You are saying option number C, right? Yes, so you are correct. So strain will increase as long as the stress is applied, but rate of strain will change with time. Why? Because as we see in the three graphs below, the graph A tells about the pure elastic material. In that, what happens when we plot the graph between the shear strain versus the time, which is our, as per the question, it is saying that when we are applying the stress, we need to monitor the strain with respect to time. So y-axis is shear strain. We are monitoring strain with respect to the time. So when we applying the stress, this is the stress we are putting stress on, right? We are putting the stress. So what is happening in the pure elastic material? When we apply the stress, so as soon as we apply the stress, the strain will be there at that particular time. If like we are holding stress for some time here, from this to this we are holding the stress, so our strain is also there, and it is instantaneously, it is coming like this, it is coming when the stress is applied, strain develops as soon as possible, as early as possible. It is, there is no time lag means, right? So what is happening, then there will be some kind of strain will be there. This amount of the strain is there in the material, and as we release the stress, shear stress is off. When we remove the stress, then what will going to happen is, at the same time the value of strain will become zero. So it will be here, right? So when we have not applied the stress, then strain will be zero. When we have applied the stress, strain, there will be some strain in the material of the pure elastic material, and as soon as the stress will remove, it will again be strain will again be zero, because the elastic material, as soon as the stress will remove, like a rubber, it will try to come into its original shape, and it will be in the relaxed state again. So there will be zero strain after we remove stress. But when in the case of the viscous material, which is a purely viscous material, what will going to happen when we apply the stress? First, there is no stress, so strain will be zero. Then, when as we apply the stress, we increase the stress, so strain will linearly increase with time. It will slowly in the viscous material, it will develop, and it will develop, and when the stress is removed, then the stress uh, then the strain will be there in the material as it is the same value, like the highest value this. So this value going to continue for the strain for some for the time being, right? And even after removing the stress, shear stress, there is the strain which is which was developed before, it will be there as it is there, like the strain will not going to be zero, it will be there in the purely viscous material. But in the case of viscoelastic material, which is having both the property, the viscous properties and the elastic property, which is our polymer also. So our polymer comes into the category of comes in the category of viscoelastic, right? So when we apply the stress, shear stress in the polymer or the viscoelastic material, what will going to happen? The strain will increase, the strain will be there in the material, right? But it will not in and it will increase, right? But it will not increase linearly as in the case of the pure viscous material. In the viscoelastic material, it will slowly increase, and when the shear stress is removed, then it will decrease. And it will also not decrease with a constant rate or linearly or instantaneously. It will not be zero, or it will not decrease like that. It will decrease slowly. The decay in the strain will be there as the stress is removed. So, as the question asked, if a constant stress is applied and the strain is monitored with time, so in a viscoelastic material, what will going to happen? So our graph C is viscoelastic material. In this, what is going to happen when the shear stress we have applied, the strain is increasing, right? Option C is saying strain will increase as long as the stress is applied, but the rate of the strain will change with the time. Our stress is increasing, but it's uh, the rate of increasing is not the same, it is different at all the points, and when the stress is removed, it will decay, the strain will be, it will slowly release from the material, and after some time it will become constant, and this much of the strain, it will be there in the material because of having the viscous component in the viscoelastic material. The elastic component, because of the presence of the elastic component, this this much amount of the strain, sorry, this much amount of the strain is has been decayed, right, from here to here in this time interval. In this time interval, this much of the amount of the strain is decayed because of the elastic component, but this much of the this amount is not decayed, right? Because of the viscous component of the viscoelastic material that will be there. So option C is correct. Now let's move to the next question. A plot of strain percentage versus time. So there is a plot of strain in y-axis versus time in x-axis of a polymer is given below. So it is given here. Based on this plot and the properties as mentioned below, find out the correct combination. So first is saying viscoelastic deformation. Second is elastic deformation. Third, viscoelastic recovery. Fourth, elastic recovery. So we need to match all these four from the different parts of the strain percent versus time curve. So the P component here, Q here, R here and S here. We need to tell which one is which one is denoting which of the part from 1, 2, 3, 4. Please, anyone? So you are saying option C is correct. This option, right? So let's discuss about this. So as per this graph, if we see what is happening is in the P and Q part, which is when the with the time the strain percentage is increasing, right? Initially the strain is in zero time the strain is this much, the O2A, right? This P amount is there, and after that strain is increasing with some different rate, right? And then strain is decreasing instantaneously, right? In no time. And then from C to D, strain is again decreasing with different rate. So we can say that till O2B, O2A plus A2B, this area, in this area, what is happening is the strain is developing. So what we can say is it is the deformation area, right? Where deformation is there. Deformation. So this area is deformation area because here strain is developing. Here strain is releasing. So what we can say from B to C and C to D, this area is the recovery area, right? The recovery area. So this is the deformation area, and the second one, the from B to D is recovery area. So we can say from this we can divide there that Q, this first and second is deformation and 3 and 4 is recovery. So we can from this we can say that either R or S will be the recovery part and and P and Q will be going to be deformation part, right? So P and Q is deformation and R and S is recovery. Now let's understand the next part. So in P, what is there? There is this strain is developing in zero time, which means it is saying that there is a elastic deformation, right? Because there is a strain is developing in a material and that to be in zero time. So elastic deformation. And when uh, like the stress will going to remove, so what will going to happen? It will regain its original shape and size when the stress is going to remove. So since it is getting the strain under the influence of a constant stress in no time, so it is a elastic deformation. So P is going to be the second V, which is elastic deformation. Okay. Afterwards is, now understand Q. Now second is, it is getting strain, which is the, it is getting this deformation, but it is having like it is, and the strain is also increasing in the material, but it is not linear. It is having some, with the some rate it is increasing, right? So it is the time dependent viscous deformation is there, right, in Q. So we can say Q is viscoelastic deformation. Next is the R and S. So R is the strain is there, which is decreasing. So recovery is there, and in no time it is decreasing. So it is again elastic recovery, because the strain is recovering in or decreasing in no time. So it is, as the stress is removed, the strain is um, like it is decreasing, and the material is trying to come in the original shape and the size. So it is showing the elastic property. And the S is, it is showing that the viscoelastic recovery, because it is taking time to recover, right? It is taking some time to decrease the strain, and uh, it will not be completely zero. The D point stops here. So this much of the strain will be there in the material always. So this is the viscoelastic recovery, right? So we can say that Q is the viscoelastic deformation, P is the elastic deformation, S is the viscoelastic recovery, and R is the elastic recovery. So we can say P is denoting 2, Q1, R4, S3. So which option is correct from this? I think D option, right? So D option is the correct one. You understood why D option is correct? Why not C? So can we move to the next question? So let's discuss next question. The change in stress of a polymer as a function of time at a fixed strain is known as fatigue, creep, stress relaxation, fracture toughness. So it is saying that the change in the stress of a polymer. So in a polymer, the stress is changing as a function of the time, and the strain is fixed now. Means stress is changing, stress is changing with the time, and strain is fixed. It is constant. So what is known as this? Fatigue, creep, stress relaxation, fracture toughness. So it is there in the slides, lecture slides. It has been discussed. So anybody? So it is the definition of stress relaxation. The option C, right? Yes, you are correct. So what happens is, polymer. fatigue, which is the option A, it is actually the process of damage caused by repeated cyclic stress or load. When we apply the stress or the load in the cyclic way or in the repeated way, then what if there is some kind of the damage is caused to that material, uh, the fatigueness is there in that material or the polymer, it is known as the polymer fatigue, right? So for fatigue is nothing but cyclic. When we apply cyclic stress or strain, then what is the damage in the product? Creep means, creep is the tendency of a solid material to deform permanently under the influence of constant stress. And the stress can be of tensile stress, compressive stress, shear stress, or flexural load. So creep is nothing but it is when there is a constant, it is not the cyclic stress load. It is the constant stress when we apply, then there is some kind of the deeper permanent deformation in the material or some kind of the strain develop in the material is known as the creep. Fracture, fatigue, fracture toughness is the material's resistance to crack propagation. So when there is a crack and it is propagating, so how much that material is trying to resist it. So it is known as fracture toughness. And finally, our answer, stress relaxation is nothing but it is a time dependent decrease in the stress under a constant strain. When there is the constant strain, then how a stress is decreasing with a or changing with the time is the stress relaxation. So our option C is correct. Next question is, which of the following expressions is correct for the Maxwell model of linear viscoelasticity? So Maxwell model of linear viscoelasticity is very important and it is well being discussed in the slides. So the question says, which of the following expresses about the Maxwell model of linear viscoelasticity? Sigma, which is the stress, and uh, E, this is the strain. So stress is equals to sum of the individual stresses in the spring and the dashboard. First option is saying this. B is saying that all the stress which is in the spring and the dashboard, it is equal same with the overall stress. Option C is saying the strain will be same in the spring and the dashboard and the overall strain will be same. Option D is saying the rate of the change of the strain is same in the overall in the spring and in the dashboard. Which option is correct? Anybody? B option, that stress is same in the spring and the dashboard and overall, right? Let's see the answer. So yes, you are correct. Option B is correct. So uh, this figure which is on the right hand side. It is showing the Maxwell model. So this is the spring part and this one is the dashboard. So they are in the Maxwell. They are being arranged in the series, right? Series. So they are arranged in series. So elastic. element, which is the spring. From spring, we are denoting that in the total material are polymer and is the viscoelastic material, right? So what is happening? We are taking its elastic component and we are denoting the elastic component with the help of the spring. So elastic element is being uh, expressed with this diagram, in this diagram, as a spring, and then the viscous component uh, or the viscous element is being understood by the dashboard, which is this bottom one, and they are arranged in basically the series. I'm sorry. So they are being arranged in the series in the Maxwell model. The viscous and the elastic component, which are the spring and the dashboard, they are arranged in series. And then in the Maxwell model, what it says, the overall stress will be equal in the stress in the spring and will be going to equal stress in the dashboard. So whatever the stress in the spring and the dashboard, they'll be equal to the overall stress. Whereas overall strain, it will be the sum of the strain in the spring and the dashboard. So option B is correct because overall stress, it will be equal in the spring, uh, dashboard and the overall, right? Whereas the strain, sorry, the strain we are denoting by E. So the strain will be equals to strain in the spring plus strain in the dashboard, right? So the option, this option is also incorrect because it is equal. This option is also, C option is incorrect, and this is also incorrect. Next is this Maxwell model. It predicts the stress relaxation behavior well, whereas the creep, it does the uh, poor prediction of the creep behavior, right? And how we denote, like there is this expression of the stress with the time, how it is changing. So for a constant value of the strain, and the strain or the strain rate equals to 0, so both means the same, right? We are saying that the strain is constant and the strain rate is equals to 0. At that time, the stress in the spring will gradually reduce with time, right? And how it will, the stress, how it will decrease? So the stress at the time t is equals to stress at initial, and it will decay the exponentially. So exponentially, bracket minus t by this tau naught is nothing but the relaxation time. So it is a function, this stress at any time, it will when we have the constant value of the strain, then what will happen? The stress will in the spring, it will reduce exponentially, like stress at any time is equals to stress initially into exponential minus t time anytime divided by relaxation time, right? By this expression, it will going to, the stress will going to reduce in a spring, right? So this is nothing but this is our Maxwell model, which is a mechanical model of denoting how the viscoelastic, like how how we can treat viscoelastic material, and how the stress and the strain will be changing in a viscoelastic material. So can we move to the next question? Are you following? So next is, which of the following expressions is correct for the creep response as predicted by the Kelvin-Voigt model of linear viscoelasticity? So our second model is Kelvin-Voigt model. First is Maxwell model in any material which is a linear viscoelastic material or a viscoelastic material. So which of the expression is correct for creep response as predicted by the Kelvin model of linear viscoelasticity? So option A, B, C and D having several this uh, relations between the stress and the strain and the modulus. Like the strain is equal to, in option A says strain is equals to stress, constant stress divided by the modulus multiply 1 minus exponential minus t, which is time, divided by the relaxation time, which is tau naught. B option is saying strain is equal to stress divided by modulus multiplied by exponential minus t time by tau naught, which is relaxation time. C is saying that dE by dt, which is strain, rate of change of the strain with time, is equals to stress by viscosity. Neta is viscosity. D is strain is equals to stress by modulus. So, which is correct for telling the creep response. It is also very important concept. Please tell. Okay, so let's discuss about this. So, what happens in the Kelvin-Voigt model? In this model, what happens? This spring part, which is denoting the elastic part, elastic element in a viscoelastic material, and the dashpot, which is a viscous element in a viscoelastic material, they'll be there in parallel now in the Kelvin-Voigt model. So elastic element, which is a spring, and the viscous element, which is a dashpot, they will be in parallel, right? And what in this, what is going to happen? The overall strain will be equals to strain in the spring, which is equals to strain in the dashboard. So here the strain will be, it will be the same, the overall strain, it will be the same in the spring and the dashboard. In the Maxwell model, what happens? These two goes in the series, spring and the dashboard, and the stress, overall stress was equal. Here the strain will going to be equal in Kelvin-Voigt, and then overall stress, which is the stress is going to be the sum of the in the spring and the dashboard. So here strain will be going to be equal and stress will be in the summation. It will, and then in the Kelvin-Voigt model, what happens? It predicts well the creep behavior, whereas it will give the poor prediction of the stress relaxation. So in the Maxwell model, as we discussed previously, it predicts well the stress relaxation behavior, whereas it poorly predicts the creep behavior. Whereas in the Kelvin-Voigt model, the creep behavior is predicted well, whereas the stress relaxation behavior is not predicted well. So these two models, they are telling, like they are predicting two different things. and well, but not the same thing. So what happens in this? If the stress is constant here, in the previous case, in the Maxwell model, we took the strain as constant. Here we are taking stress as constant. So when we are applying the stress at a constant, which is sigma naught, and the initial strain will going to be 0, upon removal of the stress, when we will remove the stress, the strain decays exponentially with time, with a constant time, which is the relaxation time. So what is going to happen here? We are taking the stress constant and the strain, and when we are removing the stress, the strain will decay as a exponentially, it will going to decay. And in the Maxwell, whereas in the Maxwell model, the strain is constant, the strain value is constant, and the stress, it is decaying with the time, exponentially decaying with the time by this relation, right? Whereas in Kelvin-Voigt model, option A is correct. So the strain is decaying with time by this relation, where strain is equals to stress by modulus, which is the stress at time t, is equal to strain initial strain, we can say, or we can say the constant stress divided by modulus 1 minus, which is and it is exponentially decaying, 1 minus exponential multiplied exponential minus t by tau naught, which is relaxation time, right? So here strain is decaying, their stress is decaying, right? So you understood both the models, Kelvin-Voigt and Maxwell model, which is very important for today's understanding of the lecture. Can we move to the next question? Okay. So we are moving to the next question. A viscoelastic material is held at a fixed tensile strain of 0.4. The short-term elastic modulus of the material is 4 megapascal and the relaxation time is 200 days. Assuming Maxwell model to be applicable, the value to which the stress decays after 250 days. So we have a viscoelastic material which is having both the viscous and the elastic elements, and it is held at a fixed tensile strain. So we have fixed strain of 0.4. So at a fixed strain, that viscoelastic material is being held, right? And the short term elastic modulus value is given as 4 megapascal. The relaxation time, which is tau naught value, is given as 200 days. We need to apply the Maxwell model, which was our first model, and then we need to calculate the value of the stress decay after 250 days. So please try to solve this question. So I can give you hint like this formula is going to apply, because we are saying that Maxwell model is going to apply, and we need to see if all the values are given and which values we need are not given, and we need to calculate. So let's solve this question. So according to the Maxwell model of linear viscoelasticity, the stress relaxation behavior equation is this. The stress at time t is equals to initial stress multiply exponential of minus t, which is at any time, divided by the relaxation time, which is nothing but it, we can say it is equals to the mod, like what we can do is we can write this constant stress. Stress is nothing but strain into modulus. So modulus into the initial strain, we can write here in place of the constant stress multiply by exponential of minus t at any time divided by the relaxation time. So let's see what are there in our question. So we have this modulus, elastic modulus value as 4 megapascal. So what we can do, we can just put here as 4 multiply the strain, which is the constant strain given in the question as 0.4. So we can multiply 4 into 0.4 into exponential of minus t. T is at which time we need to calculate is 250 days. So 250 here divide by this is 250, right? Stress decays after 250 days time. So 250 divided by 200, which is nothing but our relaxation time. So we will put in the denominator 200. Now we can just solve. This is exponential minus 5 by 4, right? Minus 5 by 4. So here it is 4, 4, 16. So 1.6. So 1.6 into exponential minus 5 by 4. So when we solve, we're going to get 0.46 megapascal as our stress after stress which decay after 250 days time. So our stress which is being decayed after 250 days time will be 0.46 megapascal. So you understood the question? Next, let's move to the next question. The relaxation time of a rubber band at 23 degrees Celsius is 60 days. If it is stressed to 2 megapascal initially, then the time required before the stress relaxes to 1 megapascal is days, dash days. So the relaxation time of a rubber band is given as 60 days. So tau naught is given the relaxation time, right? 60 days. If it is stressed to 2 megapascal, so our constant stress value is given as 2 megapascal. Then the time we need to calculate, time required, time we need to calculate before the stress relaxes to 1 megapascal. So it is saying that after some time the stress is decayed and it is now 1 megapascal. These three values are given and we need to calculate at what time this stress will going to decay to 1 megapascal. So almost the same formula we need to apply. So according to the Maxwell model of the linear viscoelasticity, the stress relaxation behavior is given as the stress at any time equals to stress at initial point multiply exponential of minus t by tau naught. This is tau naught, which is relaxation time. So where sigma is the stress after time t, 1 megapascal it is given in the question. sigma naught, which is initial stress, is given as 2 megapascal, and the tau naught, which is the relaxation time, is given as 60 days. So we can put sigma, which is 1 megapascal stress after some time, equals to initial stress, which is 2 megapascal, multiply E to the power minus T is not given, divide by tau naught, which is given as 60 days. So when it will go here, it is nothing but 0.5. So E to the power minus T by 60 equals to 0.5. Now we'll take log both sides. So minus T by 60 equals to ln 0.5. T is equals to 0. This ln 0.5 is nothing but 0.6932, right? So multiply by 60. So ln 0.5 is minus 0.6932, right? This minus 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 will going to be plus. So 0.692 into 60 equals to 41.6 days. So this is the time when our stress will be 1 megapascal. It will decay from 2 megapascal initial stress to 1 megapascal in time 41.6 days. So let's move to the next question. The behavior of a polymer is described by a Maxwell model consisting of a spring element of modulus 10 to the power 10 Pascal in series with a dashpot of viscosity 10 to the power 12 Pascal second in the solid. 50 seconds after the sudden application of a fixed strain of 1%, the stress will be. So the behavior of a polymer is described by Maxwell model. So we need to apply Maxwell model here in the question. It is saying that one polymer which is behaving like a Maxwell model, which is having one spring, which is having the modulus of 10 to the power 10 Pascal in series with a dashpot, which is having viscosity 10 to the power 12 Pascal second. So we have modulus and viscosity of the spring and the dashboard. So in that solid, 50 seconds after the sudden application of a fixed strain of 1%. So fixed strain is fixed at 1% and the time is also given as 50 seconds. We need to calculate the stress value. So let's see how we're going to solve. So in the Maxwell model, strain is 1%, time is 50 seconds, modulus is 10 to the power 10 Pascal and viscosity is 10 to the power 12 Pascal second. So the stress relaxation equation of the Maxwell model will apply, which is nothing but sigma equals to, which is the stress at any time is equals to stress initial multiplied by exponential to the exponential bracket minus E by mu t. How we wrote it? This value, the modulus divided by viscosity here, which is E and mu. So this is nothing but it is equals to the relaxation time. So it is said that we have seen the equation as sigma equals to sigma naught exponential minus t by tau naught. This equation we have seen the Maxwell equation, right? So this tau naught, which is the relaxation time, it is nothing but it is equals to this, equals to the viscous element, which is mu, divided by the modulus of elastic element, which is E. So when we write, it will be mu at the denominator, E at the numerator. So this equation will look like this. Now We just need to apply this equation and solve. So sigma, which is the stress at the time t, is equals to, which we need to calculate, equals to the stress at initial. So stress can be written as strain into modulus, right? So strain is nothing but it is given in the question at 1% or 0.01 multiply by the modulus, which is given in the question as 10 to the power 10 Pascal. So we can write multiply by 10 to the power 10 Pascal. So it will nothing but 10 to the power 8 Pascal will be the going to the stress at initial. So 10 stress at time t is equals to stress at initial, which is 10 to the power 8 multiply by exponent, then whole multiply by minus minus the modulus, which is the elastic modulus 10 to the power 10 Pascal, which is at the numerator, and then denominator is the viscous element, which is 10 to the power 12 Pascal second, multiply t at t, which is the 50-second time. At 50-second we need to calculate. So multiply by 50. So if we see 10 to the power 10 in the exponent part, 10 to the power 10 is cancelled by this. Here it will be just 100 at the denominator, and if we see it will be 50 by 100 in the in the exponential, and which is nothing but we can write it as minus 0.5, and exponent minus 0.5 and whole multiply by 10 to the power 8, which is nothing but the stress at 50 second is nothing but it is equals to 6.065 into 10 to the power 7, right? This is this much Pascal. Can we move to the next question? Okay. The short-term elastic modulus of the material is 6 megapascal, and the stress time and the relaxation time is 250 days. So the elastic modulus, the short-term elastic modulus is given as 6 megapascal. The tau naught, which is the relaxation time, is given as 250 days. Now we need to apply the Kelvin-Voigt model and describe the creep behavior of the viscoelastic material. If the material is held at constant stress 0.6 megapascal, and the time when the strain will be 0.05. So strain value is also given, stress value is given. We need to calculate time when this strain will be there, right? So in the Kelvin-Voigt model of the linear viscoelasticity, the creep, sorry, the creep behavior will be can be given by this equation, which is we have already discussed that strain at any time is equals to stress at initial or divide by modulus, which is nothing but the strain at initial multiply by 1 minus exponential minus time divide by the stress relaxation time or the relaxation time. So in this equation we have this, the strain at time is equals to 0.05 we need to calculate. So strain at time t is equals to 0.05 is equals to stress, which is given in the question constant as 0.6 megapascal. So 0.6 megapascal divide by the modulus, which is 6 megapascal here, So we'll put in the denominator this, multiply by 1 minus exponential minus time we need to calculate, this we need to calculate, and then relaxation time is 250 days, it is given in the question. This data is also given in the question, so this we can put, right. So when we solve this, we'll get 1 minus exponential minus t by 250, and this part, this 6 will go here and this 0.6 will come here. So 0. This will be 0 0.05, 0.05 multiply 6 divide by 0.6. So it will nothing but, they will cancel and it will give 0.5 here. When we subtract 1 minus 0.5, it will be 0.5 only. So exponential minus t by 250 is equals to 0.5. So t by 250 equals to minus ln 0.5, which is nothing but 0.69315. So time will be 0.69315 multiplied 250, which is nothing but close to 173 days. So this we have calculated. We are moving to the next question, which is about creep compliance. So the creep compliance of a viscoelastic polymer is given by this equation. This is now creep compliance. This is not creep, this is creep compliance, which is denoting by J at time t equals to J naught initial creep compliance multiply 1 minus exponential minus t by tau naught, which is the relaxation time, where J naught, which is the initial creep compliance, is given as 5 into 10 to the power minus 9 meter square per Newton, and the stress relaxation time is given as 500 second. If a constant tensile stress is applied of 40 megapascal, so is applied instantaneously at t equals to 0 and maintained thereafter, the time after which the strain is 0.15 is. So we need to calculate time at which the strain value will be 0.15. So we have the creep compliance of a viscoelastic polymer is given as this by this equation, right? And these are the different values is being given, and we need to calculate the time after which the strain value will be 0.15. Now let's see the, yes, 693.15. Yes, your answer is correct. We are solving this. How we are solving is we are applying Kelvin-Voigt model for creep behavior. So which is nothing but the strain at any time is equals to the creep compliance into the stress. In the question is the uh, creep compliance at 0 time or the initial multiply 1 minus exponential minus t by tau, time t means time, tau is stress, sorry, the relaxation time multiply by sigma, right? Is given in the 5 here equals to the J naught value, which is the creep compliance at initial time, which is 5 into 10 to the power minus 9 multiply 1 minus exponential minus t, at any time t we need to calculate, divide by 500, which is the tau naught value, which is the stress relaxation time value, multiply by the stress value, which is the sigma value, 40 megapascal, which is 40 into 10 to the power 6 pascal. So we have taken this value, and now let's calculate. So 0 point, when we take this exponential, to 1 minus exponential minus t by 500 is equals to 0.5, 0.15, 0.15 divide by 5 into 10 to the power 9, sorry, 10 to the power minus 9, and multiply here in denominator 40 into 10 to the power 6. So when we solve, it will be 10 to the power 6. So it will be 0.75. So when we multiply, when we minus 1 minus 0.75, it will be 0.25, and we can take log both sides. So log 0.25 is nothing but 1 minus 1.3863, minus minus will be cancelled, and t will be 500 multiply ln 0.25, which is my 1.3863 multiply 500, which is t is equals to 693 seconds. So your answer is correct, and we are moving to the next question. For a polymer sample with a viscosity of 6 into 10 to the power 11 poise, if the apparent plateau modulus of 3 into 10 to the power 6 dyne per centimeter square drops to 0 above a certain temperature, the relaxation time of the polymer is in days. So, for a polymeric sample, we have the viscosity given as 6 into 10 to the power 11 poise. And if we have the modulus value as 3 into 10 to the power 6 dyne per centimeter square, and it is dropping to 0 above a certain temperature, we need to calculate the relaxation time for that polymer. Please try to solve. 2 into you, the minus 5 seconds में you are giving answer. Here in days it is being asked. Okay, let's calculate. So we need to apply here the Maxwell model. For the Maxwell model, the stress relaxation is given as the stress relaxation modulus is equal, sorry, the stress relaxation is equals to the viscosity divided by the stress relaxation modulus. So here in the diagram also we can see this G. Here we are taking E or G, we can take anything, modulus E or capital G, which is the spring modulus, uh, and it is being in series with the this dashboard, which is having the viscosity element in it. So it is the viscosity element, and the spring is elastic element. So as per the equation, the stress relaxation, which is the tau, is equals to the viscosity element Uh, so the viscosity is nothing but 6 into 10 to the power 11 poise, or 6 into 10 to the power 10 Pascal second. So divide 6 into 10 to the power 10 Pascal second, divide by the relaxation modulus, right, which is 3 into 10 to the power 6 dyne per centimeter square, or 3 into 10 to the power 5 Pascal. So we can divide both of these and we get this. So you said correctly 2 into 10 to the power, you said minus 5, it's plus 5 seconds. So 2 into 10 to the power plus 5 seconds is the answer, and we can divide it by 60 into 60 to get the 55.55 hours, which will further divide by 24 to get 2.3 days. So this is our answer. So please see that is it 2 into 10 to the power minus 5 seconds, or 2 into 10 to the power plus 5 seconds, because I think it's plus 5 seconds. Okay, so we are moving to the next question, which is about the viscoelastic polymer. So it is basically a question related to the Boltzmann superposition principle. So a viscoelastic polymer is subjected to the following stress loading history, and like a viscoelastic polymer is given, and all these three conditions are applied. Like at t equals to 0, the constant stress of 10 megapascal is applied instantaneously on the polymer and maintained from t equals to 0 to t equals to 100 seconds. So from 0 to 100 seconds, 10 megapascal of the force is stress is being applied, and in the second stage, at t equals to 100, the applied stress is increased instantaneously to 20 megapascal and maintained constant from 100 to 150 seconds. So from 100 to 150 seconds, 20 megapascal force is applied, and in the C part, from 150 seconds, the stress is reduced instantaneously to 5 megapascal, and from t 150 to 300 seconds, 5 megapascal of the force is being applied. If the creep compliance of the polymer is given by this equation as this equation, so where creep compliance at any time is equals to creep compliance at 0 time multiply 1 minus exponential multiply minus t by tau naught, which is relaxation time, where the creep compliance at a 0 time is given as 4 into 10 to the power minus 9 meter square per Newton, and relaxation time is given as tau naught equals to 150 second, and we need to apply the strain in the polymer at t equals to 250 seconds. So after 250 seconds, we need to answer what is the strain value. So please, can we solve? So first let's draw the curve. So we are taking the x-axis as time and y-axis as the stress in the megapascal. So first 0 to 100 seconds, it is said that we need to apply 100 megapascal. This 0 to 100 seconds, 10 megapascal is being applied. So 0 to 100, 10 megapascal is applied. And then from 100 to 150 seconds, 20 megapascal is applied. So 100 to 150, 20 megapascal is applied, and afterwards From 150 to 300, 5 megapascal is being applied, right? These three conditions is being given, are being given. So when we apply the Boltzmann superposition principle for calculating the strain in the polymer at t equals to 250 seconds. So strain at 250 seconds is equals to, in the Boltzmann superposition principle, what happens? It takes into account the whole history, right? So is equals to the, it will going to be equals to the strain due to the, due to this one stress from 0 to 100 second, then plus stress, plus strain which is during 100 to 150, and then the strain because of this last one, which is the 150 to 300 seconds. So it will, what it will do, it will, in the Boltzmann superposition principle, it will take account all the history of the strain. Like strain we are calculating at 250 seconds, which is nothing but it will be somewhat here, right? So it will take into account this whole history, right? So strain at 250 seconds is equal nothing but it is equals to the change in the stress delta sigma 1 in the first condition. So from here to here, how much it is changed, which is multiply by the creep compliance at the 250 seconds minus the tau 1, which is the at first time, uh, what is the value, plus, so plus the sigma naught, sigma 2, which is the, sorry, plus delta sigma 2, so which is the change in the stress at the time when the second cycle is there, right? So this value will be there, this is the value. So 20 megapascal, from 10 it will, the stress goes to 20. So this value will be there, multiply by creep compliance 250 minus the tau 2. Here in this tau value is going to be changed, because for this 0 is the base, right? From 0 it this stress is applied. Afterwards 0 will not be there, right? Then 100 will be there. From 100 this stress is being applied. So the initial point at which that particular stress is being applied, we'll going to calculate this, because here we need to take the from 250 to tau 1. So because the sigma 1, the stress sigma 1 is being applied from t equals to 0 to 100 second. So minus tau 1. So tau 1 will nothing but it is 0. So the base value from which the stress is being applied, it is being taken as tau 1. Or then in second case, the tau 2 will be nothing but it will be 100, because the second sigma 2, which is the 20 megapascal, is being applied from 100 seconds to 150 seconds. So 100 will be the, because the base value sigma delta sigma 3, which is the 5 megapascal last force is there, multiply by creep compliance at 250, because 250 at the time we need to calculate after 250 seconds. So 250 minus tau 3, which is nothing but 150, because the 5 megapascal force it is come into the picture from t equals to 150 to 300 seconds. So base value is 150. So from 150 it is being calculated. So the strain at 250 is equals to 10 megapascal, which is nothing but the sigma one value, delta sigma 1 value, which is 100 minus 0, right? Because from 0, this force is, this stress is applied, and it is 10 up and reached to 10 megapascal. So 10 megapascal into में creep compliance, which is J at 250 minus 0. Why? Because 250 is the time we need to calculate. So 250 minus 0, because this stress is being applied at t equals to 0 to 100 seconds. So t equals to 0 is the, from, so at from 0 this force of 10 megapascal or the stress of 10 megapascal is being applied. So the base value of time is 0. So it is being started at 0 time. So 0 is being taken plus delta sigma 2, which is the this value. So it is applied 20 megapascal. So 20 megapascal minus 10 megapascal, because sigma 2 is this value. After 10 megapascal, this is increased to 20 megapascal. So what will going to be there? 20 megapascal minus 10 megapascal will nothing but 10 megapascal multiplied by creep compliance, which is at 250 minus tau 2, which is 100. So why 100 is because this 20 megapascal force, or the stress is being applied at the time equals to 100 to 150 seconds. So the base value is 100. So from 100 second is this stress is being applied. So 250 minus 100 plus this value plus sigma delta sigma 3. So now from 20 megapascal, this is coming down. So the stress is coming down. So what will be there? Delta sigma 3 will nothing but it will be 5 minus 5 megapascal minus 20 megapascal, because sigma 3 is 5 megapascal minus में this sigma 2 value is 20 megapascal, so which will nothing but minus 15 it will give. So 15 minus 15 megapascal into J, which is the creep compliance, multiply, which is at time 250 minus 150, because this 5 megapascal force is being applied from 150 to 300 second. So base is 150, from 150 second it is being applied. So 250 minus 150. So after simplifying, we'll get the strain at 250 seconds is equals to 10 megapascal into creep compliance at 250 seconds plus 10 megapascal into creep compliance at 150, because 250 minus 100, which is nothing but 150, plus minus 15 megapascal into creep compliance at 250 minus 150 is nothing but 100. So at 100 seconds. Now we need to calculate all these creep compliance at different time. So which is the creep compliance of different polymer is given by this equation at any time. So creep compliance at any time is equals to creep compliance at initial time multiplied 1 minus exponential minus t at any time divided by the stress relaxation time. So for 250 seconds, J 250 will nothing but equals to J naught, which is 4 into 10 to the power minus 9 given in the question, multiply 1 minus exponential minus t is nothing but 250 in this case, divide by the relaxation time, which is nothing but tau naught is nothing but it is 150 seconds. So divide by 150. So this value will going to give the creep compliance at 250 second is nothing but 4 into 10 to the power minus 9 into 1 minus, this is exponential minus 5 by 3, which is 0.111887, right? So 1 minus 0.1887 will minus and will multiply by 4 into 10 to the power minus 9, and it will give the creep compliance at 250 seconds is to 3.24 into 10 to the power minus 9 meter square per Newton. Same we will be going to calculate for this creep compliance value at 150 and time 100 seconds. So creep compliance at 150 second is equals to J naught, which is 4 into 10 to the power minus 9 multiply 1 minus exponential minus the time, which is 150 seconds, and divide by the stress relaxation time, which is 150. So this will be cancelled. It will be exponential minus 1, which is nothing but 0.3679. So, when we minus it with 1 and multiply with 4 into 10 to the power minus 9, we will going to get creep compliance at 150 seconds is equals to 2.528 into 10 to the power minus 9 meter square uh, per Newton. And we'll calculate for hundreds time equals to 100 second. The creep compliance is equals to J naught, which is the initial creep compliance, 4 into 10 to the power minus 9 multiply 1 minus exponential minus the time at 100 seconds divided by the stress relaxation time 150. So this will be 10 by 15. So 10 by 15 is 2 by 3. So exponent minus 2 by 3 is equals to 0.134 this value. So it will be minus 1 and multiply by 4 into 10 to the power minus 9. We're going to give the creep compliance at 100 seconds is equals to 1.946 into 10 to the power minus 9 meter square per Newton. And all these values, say from the equation 2, which is the creep compliance at 250 seconds. In the equation 3, the creep compliance at 150 seconds and creep compliance at 100 seconds. From the equation 4, we'll take this and we'll put it into this equation 1, and uh, this will then look like the strain at 250 seconds is equals to stress, which is 100 megapascal, into this value we'll put 3 into 2.4 into 10 to the power minus 9 J250 value. So plus 100 megapascal into J at 150, which is 2.528 into 10 to the power minus 9 plus minus 15 megapascal into J 100, which is 1.946 into 10 to the power minus 9. So when we solve this, we get the strain at 250 will nothing but equals to 28.49 into 10 to the power minus 3 strain. So this is our answer, the strain at 250 seconds. So have you understood this question, the Boltzmann superposition question? So what is happening is when we are applying the stress um, in different time intervals like 0 to 100, we are applying 10 megapascal. Then we are applying 100 to 150 seconds, uh, 20 megapascal, and then from 150 to 300 seconds, we are applying 5 megapascal. We are decreasing the stress and we are applying now 5 megapascal force or the stress. Then there are different strains will develop in that material, and the strain is going to be calculated, and it will take the strain at 250 will going to take the um, summation of all the strains which is due to the history. So, for this, we applied Boltzmann superposition principle, and we applied like what we did is we took the different stress value which is being applied at different time. We took the like the we took the delta strain value like from 0 to 10 megapascal. First stress will be applied, so we took 10 minus 0, which is 10 megapascal delta sigma 1, and delta sigma 2 is we took 20 megapascals divided by 10 megapascal, which is again 10 megapascal, and sigma 3 we have taken 5 minus 20 megapascal because the change is like from 20 megapascal, the force is now 5 megapascal. So 5 minus 20, which is nothing but minus 15 megapascal, and we multiplied with the different compliances and we calculated the creep compliance by the equation given in the question, and we put all these in the equation of the strain, all these compliance value after calculating, and then we got our strain at 250 seconds. So you understood this question? This is a bit lengthy question. Okay, so we are moving to the next question. If a sinusoidally varying stress is applied to a viscoelastic material, then A, strain is in phase with the stress and oscillates at the same frequency as the stress. B, strain is in the phase with the stress but oscillates at a different frequency than the stress. C, strain always lags the stress by a phase angle of 90 degree and oscillates at a different frequency than the stress. D, strain lags the stress and oscillates at the same frequency as the stress. So when we are applying the sinusoidally, which is in the sine, like the wave in the sine wave equation, we can say, or in the sine wave form, we our wave is our stress is we are applying in a sinusoidally varying stress. Then in a viscoelastic material, then what is going to happen? It is a question of like oscillating stress when we apply in a viscoelastic material. Anybody? Please, can you say loud? Your voice is not clear. D. So your answer is correct. How what happens is in a perfectly elastic material, the strain is the, the strain is in the in phase and oscillates at the same frequency as stress, which is the option A. So option A, which is the strain, will be there in the same phase and with the stress, and it will oscillate with the same frequency. With the stress is for the perfectly elastic solids, not for the viscoelastic material. For Newtonian liquids or completely viscous material is there, then strain is in the phase with the stress, but it will lag by phase angle of pi by 2 radian. So uh, it is for the viscous response. And for the viscoelastic response, what happens? Strain lags the stress by some phase angle, which can be between 0 to 90 degree. Stress can be given as sigma equals to sigma naught sine omega t plus phi, sorry, plus some angle, and then which is delta angle, which can be between 0 to 90, and strain will be equals to strain into sine omega t. So this will be having this phase and difference of uh, delta phase separation is there. So strain is lagging behind and stress is ahead by some phase angle. So option D is correct. Match plots 1 to 4 given in the figure below with the correct flow behavior of polymeric fluid listed as PQRS. So P is Newtonian, Q shear thickening, R pseudoplastic, S Bingham plastic. So these are our plot. In this there are these different lines, and in x-axis stress is there, in y-axis the rate of shear is there, and we need to tell when we are plotting the shear stress against the shear rate. So, which type of the polymer fluid will behave, Newtonian or the Bingham plastic or the shear thickening or the pseudoplastic, how it behaves? Anybody? A. Let's see. So, what happens is Newtonian fluids are the fluids basically where shear increases linearly with the stress, where this line number 3, where the shear stress and the rate of shearing is having the linear relation. When they are increasing, like when the shear rate is increasing, shear stress is also increasing, and shear stress is increasing, then shear rate is also increasing linearly, then it is the Newtonian. So line 3 is denoting the Newtonian line, and the shear thickening, which is also known as the dilatant fluids, they shows when viscosity or the stress increases with the shear rate. When we are applying the shear rate, some shear rate is there, then the stress or the viscosity, it increases. So it means it is a shear thickening or the dilatant. So shear thickening is denoted by the 4 line, which is this line. As we are increasing the rate of shearing, the stress or the viscosity goes on increase in this. In shear thinning or the pseudoplastic, uh, sorry, it is shear thinning or pseudoplastic. So in this what happens is viscosity or the stress decreases with increase in the shear rate. So when the shear rate increases, the viscosity decreases. So which is denoted by the 2 line. The pseudoplastic is 2, because as we see that the stress, it as we are increasing, the curve is making like this. It is decreasing. It will go like that. Decrease it. The value will going to decrease for the stress or the viscosity. And in last is the Bingham plastic, which is the line number 1, which denotes like first the resistance will be there in the deformation up to a certain stress, and then it shows the Newtonian behavior. So this is the yield stress. After the yield stress, it will behave linear like a the stress will be linearly related to the strain. So it will be behaving like a Newtonian fluids after the yield stress. So P is 3421. So which option is correct? 3421. Option B is correct actually, not the A1. So have you understood? Are you following? Okay, so let's move to the next question. Which of the following trends is the most appropriate for a thixotropic fluid? A. Viscosity increases with increase in the rate of shear. B. Viscosity increases with increase in the time of the application of shear. C. Viscosity decreases with increase in the time of application of shear. Or option D. Viscosity increases with decrease in the rate of shear. So it is saying that thixotropic fluid. So what happens with the thixotropic fluid? So option C is correct. What happens in the thixotropic fluids? Viscosity actually decreases when we apply the stress over a known period of time. It shows a time dependent pseudoplastic behavior or the shear thinning behavior with the time. Whereas in the rheopactic fluids, what happen is viscosity of the fluid, it increases with the stress over the time. So it happens, it is also a time dependent fluid and it behaves like a dilatant or the shear thickening behavior, but with the time, right? So what is the correct answer? C. So thixotropics are one which is having the decreasing viscosity with increasing in the time of the application of the shear. So we can see in the graph also the viscosity on the y-axis and the x-axis is time. So if it's a time independent fluid, so with the time the viscosity will be constant, right? It will be showing straight line. But in the case of the thixotropic, with time the viscosity is decreasing, and in the rheopactic with time the viscosity is increasing. In the second graph, uh, the stress, the shear stress and the shear rate, if we see in the thixotropic, what happens when we increase the shear, when we increase the shear rate, the shear stress it increases, and then uh, it will not follow the same path when it come back, and its viscosity decreases or the its value is going to decrease. But in the case of the rheopactic, what happens is its value is going to increase. The like we can see it is coming by a coming back by this curve line. So this is more than the line which it is being followed in the while going. So while coming back, it is having more value. So the rheopactic is having more how more stress or more viscosity value, whereas in thixotropic the curve it followed while coming back is the bottom one. So it is decreasing. The value is decreasing for the viscosity or the stress with respect to the strain rate. So let's move to the next question. The constitutive equation of a shear thinning polymeric liquid is given by sigma equals to m rate of shear to the power n. If m equals to 10 to the power 4 Pascal second to the power n and n value is given as 0.35, the apparent viscosity of we need to calculate when the shear rate is 100 second inverse. So this is something like power law. This equation is looking like that. So what happens is, let's calculate. Everything is given. Constitutive equation of a shear thinning polymeric liquid is given as this, right? Sigma equals to m shear rate to the power n, and it is nothing but it is equals to viscosity to apparent viscosity which is a function of the shear rate multiplied by shear rate is equals to this whole value. So here from this equation we can say that apparent viscosity which is a function of the shear rate is equals to m into shear rate to the power n minus 1. So m value is given in the question as 10 to the power 4, shear rate is given as 100, and n value is given as 0.5, sorry 0.35. So we can put 0.35 minus 1 to the power 100 into 10 to the power 4, which is nothing but 501 Pascal second is our apparent viscosity. So can we move to the next question? Next is the constitutive equation of a shear thinning polymeric liquid is given by sigma equals to mu naught shear rate divided by 1 plus shear rate divided by shear rate naught. So which is naught means that uh, like this constant value is given if these constant values are given if mu naught which is equals to 50 pascal second and sigma naught sorry and shear rate um, naught equals to 40 second inverse are constant. These values are given and we need to calculate the apparent viscosity here also in this case at shear rate which is given as 50 second inverse. So 50, at 50 second inverse we need to calculate the apparent viscosity where the equation for shear thinning polymeric liquid is given as this. So the constitutive equation of a shear thinning polymeric liquid is given as this, right? Where we have some values given in the question. Now we can put sigma equals to mu naught is given as 50 pascal second. So we can put 50 multiply by shear rate which is not given divide by 1 plus shear rate divide by shear rate at shear rate at initial or not which is 40. So we can put in the equation as 40 second inverse and this whole is equals to this sigma stress is nothing but it is equals to this value which is the apparent viscosity which is a function of shear rate multiplied by shear rate. So we can put equate this equation and we can put at 50 second inverse we can calculate at 50 second inverse shear rate value we can put this and we can calculate the apparent viscosity which is 50 into 50 divided by 1 plus 50 by 40. There is nothing but it is equals to apparent viscosity into में 50 which is shear rate. So apparent viscosity is nothing but it is equals to this 50 will going to cancel by this 50. 50 so it will give 50 divided by 1 plus 5 by 4 which is nothing but 22 by 22.22 pascal second as our viscosity. So are you following? Are you getting this answer? Okay. So next is storage modulus and 10 delta of a polymer are 10 delta which is loss tangent actually of a polymer are are experimentally measured by differential scanning calorimeter, TGA, thermogravimetry analysis, thermomechanical analysis, or last is dynamic mechanical thermal analysis. So the storage modulus and the loss tangent, how we calculate experimentally. Yes, you are correct. The option D is correct. Dynamic mechanical thermal analysis. So these are different thermal analytical techniques which includes the dynamic mechanical thermal analysis which measures the viscoelastic properties as a function of time, temperature and frequency. And it helps in calculating the storage modulus, loss modulus, 10 delta, then glass transition temperature, secondary transitions also we can calculate from this. The DSC, which is the option A, is differential scanning calorimeter, and it helps to measure the heat absorbed or released during the heating or cooling. It helps in calculating the glass transition temperature, melting temperature, crystallization temperature, percentage crystallinity. The TGA, which is thermogravimetry analysis, is used to calculate the weight or the change in the weight with respect to time and temperature in an inert or reactive atmosphere. It helps in calculating the thermal and oxidative stability of a sample or the degradation study we can do from TGA. And then third is the thermomechanical analysis, TMA, uh, and it is used to calculate the change in the dimension during heating and cooling, it used to calculate the thermal coefficient, transition values of the temperature, and the stress relaxation values. So our option D is correct, because the viscoelastic properties, which are the modulus and storage modulus and the tan delta, they are being calculated with the help of dynamic mechanical thermal analysis. Next question is, from the dynamic mechanical analysis of a polymer sample with a phase angle of 30 degree, the relationship between the storage modulus and the loss modulus can be. So we need to tell the storage modulus and the loss modulus relation if the phase angle is 30 degree. Please, anybody, which option is correct? So option A is correct, as we know that loss tan delta, which is the loss tangent, is nothing but it is equals to the loss modulus divided by storage modulus, and tan delta means tan 30 will be equals to 1 upon root 3, which is equals to loss modulus divided by the storage modulus. So the storage modulus is nothing but it is equals to under root of the loss modulus. So option A is correct. Next is the question for the WLF equation. So let's see. A linear amorphous polymer has a viscosity of 5 into 10 to the power 6 Pascal second at 60 degrees Celsius. The WLF equation describing the variation of the viscosity with temperature is log 10 AT equals to minus 17.44 multiply T minus Tg divided by 51.6 plus T minus Tg. If the glass transition temperature of the polymer is 30 degrees Celsius, the viscosity of the polymer at a glass transition temperature is. So this is the WLF equation, and we need to calculate the viscosity at glass transition temperature, and Tg value, which is the glass transition value, is given as 30 degrees Celsius, and the normal temperature is given as 60 degrees Celsius, and the at 60 degrees Celsius the viscosity is 5 into 10 to the power 6 Pascal second. So we need to calculate the viscosity at glass transition temperature. So let's solve this question. As per the WLF equation, this is the equation. So log 10 AT is equals to log 10 viscosity at T temperature divided by viscosity at glass transition temperature is equals to minus 17.44 multiply T temperature minus glass transition temperature divided by 51.6 plus at any temperature T minus glass transition temperature. So we can put all this in this equation, the values, and we can calculate the viscosity at glass transition temperature. So log viscosity at temperature T is equals to 5 into 10 to the power 6. We can put in the numerator, divide by denominator, we don't know, equals to minus 17.44 multiply by 60, which is the temperature given, minus Tg temperature minus 30 divide by 51.6 plus the temperature which is given as 60 minus the glass transition temperature which is minus 30. So 60 minus 30 is nothing but it is equals to 30. So when we multiply 30 into 17.44 and we have to divide this by 51.6 plus 30, which is we need to 81.6. So when we do this, it will get minus 6.4118, and when we take the log both side and we solve, we get the viscosity at glass transition temperature is equals to 1.29 into 10 to the power 13 Pascal second. So in this equation, this WLF equation, uh, we can note that the temperatures are taken in degree Celsius, not in Kelvin. So mostly uh, in the formulas we take temperature is in the Kelvin, but here we are taking in degree Celsius because there is the difference in the temperature is involved. So uh, it will be same in the Kelvin and the degree Celsius. So we are taken in the degree Celsius, not in the Kelvin. So please see this also, that it, because it's a minus, right? T minus Tg. So we can take. So you understood this question? Can we move to the next question? So next is a linear amorphous polymer has a Tg of 10 degree, and at 28 degree it has a melt viscosity of 4 into 10 to the power 8 poise, and viscosity of the polymer we need to calculate at its Tg. So it is almost the same question what we have solved. So we can use WLF equation, and the Tg, uh, the viscosity at temperature T is given as 4 into 10 to the power 8. So log 10, uh, mm, 4 into 10 to the power 8 divided by the viscosity at Tg, which we need to calculate, equals to minus 17.44 multiplied by the time at temperature 28 minus Tg is 10. So 28 minus 10, which is nothing but 18, divided by 51.6 plus 28 minus 10. So which is nothing but 18. 18 plus 51.6, which is nothing but it will be 969.6, right? So when we solve all these things, and we can get the glass transition temperature, that glass transition temperature, the viscosity will going to be 1.295 into 10 to the power 13 poise. So this question is almost the same as previous one, just like just we are solving for our practice. And the here the values in the viscosity is different, like there it is in the Pascal second, here it is in the poise. Next is the rubbers are a class of polymers known for high intermolecular forces, high Tg, crystalline polymers, or low intermolecular forces. So it is having low intermolecular forces, because rubbers actually they are amorphous in nature, and due to high chain flexibility and branching, it is amorphous in nature, and it has a low intermolecular forces uh, because it is a amorphous in nature. And in the crystalline polymer, mostly what happens, the intermolecular forces are high, but since it is amorphous polymer, so it is having low intermolecular forces, and therefore it has low Tg also. So this next question is saying the number of network strands per unit volume in a elastomer is 500 mole per meter cube. Assuming the affine network model to apply, the work per unit volume required to extend and same elastomer to twice its original length at a temperature of 25 degrees Celsius is. 1.239 megajoule per meter cube, 3.655, or D, C is 6.168, or D is 8.532 megajoule per meter cube. So it is saying the number of network strands per unit volume is given in a elastomer as 500 mole per meter cube. We need to assume the affine network model which is applying here. So in that case, we need to calculate the work done per unit volume to extend the same elastomer to twice its original length at the temperature of 25 degrees Celsius. So we are stretching and we are doing some work and we need to calculate work per unit volume for that. When we are increasing, when we are increasing the original length to twice. Anyone saying anything? B option you are saying. So the option A is actually correct. Let's see how we are solving and why we are getting A, not B. In the fine network model of the rubber elasticity, what happens is for uniaxial deformation and assuming no volume change on deformation, the work per unit volume is given by this equation W by V, which is work per unit volume, equals to N kb into T by 2V multiplied by lambda square plus 2 by lambda minus 3. This is our equation as per affine network model for rubber elasticity. When we are applying this model, then we have this equation. So this is the number of the net, n is the number of the network strands, V is its like volume. So N by V, which is number of the network strands per unit volume, which is N by V, is given in the question as 500 mole per meter cube. So we can convert it into, like, we can multiply it by Avogadro number, which is 6.022 into 10 to the power 23, and we can get N by V value as 3.011 into 10 to the power 26. Temperature is given in the question as 25 degrees Celsius. So we can convert into Kelvin, which is 298.15 Kelvin. And lambda is given as 2 because it is saying that the length is increasing twice from the original length. So we can put in this equation all these values. W by V here, W by this equation, W by V is nothing but it is equals to N kV T by 2V multiplied by lambda square plus 2 by lambda minus 3. So W by V is equals to 3.011 into 10 to the power 26, which we have just calculated, multiplied by kb, which is value is given like it's constant, so 1.3806 into 10 to the power minus 23 multiplied by temperature 25 degrees Celsius or 298.15 Kelvin. So divide by 2 because n by v is 3.011 into 10 to the power 26, which we have already calculated, multiply by 2 to the multiply lambda, which is original. We are increasing length by twice from the original length, so 2 square plus 2 by lambda, which is 2 minus 3. So 2 this equation we will going to get, right? And what we can do, we can solve this, and here 2 square is 4 plus 1 minus 3, which is nothing but 2, right? So 2 here, and when we solve this equation whole, we get W by V is equals to 1.239 megajoule per meter cube. Also, like, we can calculate this Kb, which is nothing but a constant value. We can calculate it as equals to R by Avogadro number. So R is gas constant, which is 8.314 divided by Avogadro number, which is 6.022 into 10 to the power 23 equals to 1.3806 into 10 to the power minus 23 joule per Kelvin. The same value which we have calculated, or kb value is just known as constant, so we just need to apply the formula of the affine network uh, work done per unit volume, and we can calculate get the work done per unit volume as 1.239 into 10 to megajoule per meter cube. So our option A is correct, not option B. Now you understood why I am getting option A, not the option like B, why I am not getting 3.655, why I am getting 1.239. So I am moving to the next question now. For biaxial deformation in the x and y directions with corresponding deformation factor lambda x y equals to lambda y equals to lambda. So the deformation in the x y direction is equals to lambda, and then the deformation factor in the z direction, assuming incompressible deformation is. So if incompressible deformation is there, then what is the deformation in the y direction? So for incompressible deformation, the situation is the old deformation, the in the x direction, y direction and z direction, when it will be multiplied, it will come to 1. So the deformation in x y direction are lambda into lambda z, because lambda z we need to calculate deformation in the y z direction equals to 1. So deformation in the z direction is equals to 1 upon lambda square. So option B is correct. I'm moving to the next question. One of the strain invariants used in the derivation of the Mooney-Rivellin equation is, this is the equation for strain invariants for uniaxial deformation, assuming that there is no change in the volume and lambda x, the deformation in the x direction, is equals to 4. So the value of I2 we need to calculate. So for uniaxial deformation, and we are assuming that there is no change in the volume, so the deformation in the y direction and z direction, it will be equal, and it will be equals to 1 upon under root the deformation in the x direction, which is nothing but, which is 1 upon under root 4, which is nothing but 1 upon 2. So I2 equals to, which is given in the question, this equation, the deformation in the x direction square multiply deformation in the y direction square plus deformation in the y direction square multiply deformation in the z direction square plus deformation in the z direction square multiply deformation in the x direction square. So I square is nothing but deformation is x direction is 4 square multiply by 1 upon 2 square, which is deformation in the y square, plus deformation in the y and the z is 1 by 2. So 1 by 2 square multiply 1 by 2 square, plus deformation in the z and x. So in the z it is 1 by 2 square, and in the x it's 4 square. So I square value is nothing but it will be 8.06. So have you understood? So I am, this was the last question for today. So the topics we have covered today are viscoelasticity. We discussed about the creep and the creep compliance, and then we discussed about the stress relaxation modulus. We discussed about the two mechanical models, Maxwell and the Voigt, Kelvin-Voigt. And we discussed about the Boltzmann Superposition Principle, and then we discussed about the dynamic mechanical analysis. We also discussed about the polymer rheology, like about the non-Newtonian behavior of the polymer, and uh, the time and the temperature, sorry, the temperature and the molar mass dependence of the rheology, which is the viscosity, and of the polymeric fluids. And then we discussed about the rubber elasticity, and in that we discussed about the affine network model and the Mooney-Rivellin equation. And in that next class we will be discussing about the different polymer models, like the unentangled polymeric dynamics. We will going to discuss about the Rouse and the Zinn model, the entangled dynamics, polymer dynamics, which is like the reptation model. We will discuss about all these models in the next class, and that we will try to solve some of the questions based on that. And this is the YouTube channel link where I will be posting this recorded lecture, and the in the Google Drive link I will be uh, uploading the today's lecture slides. My email ID is shikhas.cl@iitg.ac.in, so you can write any problem if you are facing. Thank you so much for joining today's class.